Adventers, welcome back to our Advent of Code 2024 series. My name is Jatin Kumar Malik and I absolutely love solving these problems. We have been on a journey from last 18 days of going behind the scenes, reading a puzzle and trying to understand how to approach a problem like this before you start to think about how to convert it into a code. And personally, as a principal engineer who has been coding for better half of last 12 to 15 years, I think solving a problem before you jump into writing code is always a very useful skill to have. And if you are new here, please check out our playlist for last 18 days and you would love to catch up and probably you will learn some new things. Yesterday was a very interesting problem where I helped a bunch of historians to navigate through a memory that was getting corrupted by the falling bytes. And yeah, so today we are at day 19 and I'm presenting you from a non-decagon. So non-decagon is a polygon with 19 sides and we are almost approaching a full circle. And with that, let's move on and let's read problem for day 19. So the day 19 problem today is called linen layout. So today the historians take you up to the hot springs on the Gear Island. And I have heard about this. Oh, so I can see that hot springs is basically a reference to day 12 for 2023. And I remember writing a Medium blog on this, if I'm not wrong. Yeah, I remember this visualization I generated from a very early model of DALI. And this was a very interesting problem. And I think we are going to see some similarities here. But moving back, very suspiciously, and let's see what's that. So if you have played the game amongst us, you definitely know what this stone is about. So it seems like something is going to get wrong. So could this finally be your chance to visit the onsen next door? And what is an onsen? Oh, onsen. Yeah, so onsen is a hot spring and bathing facility and traditional inns around them in Japan. And I know this very well because I have been playing this game called Ghost of Tsushima. And in that, you regularly take baths in onsens while you are crafting those poems. What do they call it? Haikus. Yeah, when you're crafting those haikus. So it's a very interesting game. You should play it if you haven't. So there is only one way to find out. After a brief conversation with the reception staff at the onsen front desk, you discover that you don't have the right kind of money to pay the admission fee. Seems pricey. However, before you can leave, the staff get your attention. Apparently, they have heard about how you have helped the hot springs, probably the last year, and they are willing to make a deal. If you can simply help them arrange their towels, they will let you in for free. So it seems like we have a bunch of towels that need some kind of an arrangement to be done. I like writing things down. So if towels at this onsen is marked with a pattern of colored stripes, there are only a few patterns, but for any particular pattern, the staff can get you as many towels with that pattern as you need. Each stripe can be, so we are given a bunch of colors here. So let me write them down. So each stripe can be white, blue, black, red, and green. And blue here is marked with a U. And it says that we basically have unlimited number of towels. So there is no problem with us running out. And we have to arrange them in some pattern. So it is giving an example so that a towel with the pattern GGR would have a green stripe, and a red stripe in that order. So these are our primary colors. And then we can have some towels that can have a combination of these patterns. So we are given an example of GGR here, which will have like a green, and a red stripe in that order. And it says that you cannot reverse a pattern by flipping a towel upside down, as that would cause the onsen logo to face the wrong way. So it's very simple. The pattern, how it is given, that is how it is. We cannot reverse it or rotate it. So the official onsen branding expert has produced a list of design, each a long sequence of stripe colors that they would like to be able to display. You can use any towels you want, but all the towel stripes must exactly match the desired design. So to display the design, so we are given a design. Let's say in this example, it says RG, RG, R. So you can use multiple ways, where one of the solutions can be we can use two RG towels and one R towel, right? Like, so basically this can use three towels to do that. Or it says that we can also use, there is another solution where you can use a towel with RGR pattern and then a GR pattern where you will use two towels. And of course, this is assuming, or even a single massive. So you can even have like one towel, which will probably directly fulfill the design. But assuming that such towel pattern were actually available. I can see where this is going, but let's read on. So to start, collect together all of the available towel patterns and the list of desired designs, your puzzle input. For example, so here if we see, we are given a bunch of towels. So yeah, I have pasted this example here. And if we see here we are, these are our towel types, maybe the types of towel we have. And these are our designs that we can make. So now looking at this, it says that first line indicates the available towel patterns, and the onsen has unlimited towels with basically single red stripe, a white and a red stripe, a black, a green, a black, white, blue, because U was blue, and so on. Doesn't really matter. We only care about the alphabets that are given here or the pattern. And after the blank line, the remaining lines each describe the design the onsen would like to be able to display. In this example, the first design BRWWR indicates, so let's take the first example. So this example is BRWRR in this order. And yeah, so this is like black, red, white, red, red. And it also says that not all designs will be possible with the available towels. In the above example, the designs are possible or impossible as follows. So let's look at this example first. So looking at this, I think one of the best way to convert a code or write a code into an algorithm is to carefully observe how you solve it manually with your hand. Because see, your brain has a lot of algorithms in it. Probably you know it or not, but humans are really good at pattern identification. And once you're able to decipher how your brain is thinking, writing code is actually fairly simple. So in this case, I can try to start to see and try to qualify like what are the different patterns that I can start to make. So very quickly, I can see that I have a BR towel that can come here. And then I have a WR. So I have a WR that can fulfill this. And then lastly, if I take this color, I have a R towel which can fulfill this. So we definitely have one design. And then there can be actually different types of design where I can also go with a BRWRR. So I could have also gone with a BR and then WR and R. So that's another option that is there. And similarly, it has given us like different towels. So it says that this can be done, this can be done. Like all of these can be done, but this is impossible. So let's look at this case. So this says it's not possible to do this. I will write it down. So it's UBWU. And if I look at now, I can clearly see that I don't have any towel that starts from U. And not to confuse with this, because we cannot reverse it. It will always have to be read like exactly how it is given. So we cannot reverse it or anything. So it seems like we cannot do this. Obviously, we had a matching towel for BWU, but we don't have a single U towel or a UB towel or something like that. And similarly, there is another one called BBRGWB. And this is also not possible because GW. Yeah, so similarly, like we don't have anything for this GW. There is a single G, but we don't have a WB or W. We have a WR or we have B. So that's why this is not possible. So fair enough. So in this example, 6 of the 8 designs possible with the available towel patterns. Now to get into onsen as soon as possible, consult your list of towel patterns and desired designs carefully. How many designs are possible? Okay, I see. So in our puzzle input, we can see that we are given a bunch of towel patterns on top, and then we are given a bunch of designs below. And we basically have to find the number of designs that are possible. So it's a very interesting question, and I can already start to think about some of the theories on how I would try to solve it. But for you, I think it's a good time to now pause and think about your approach on how would you think about solving the problem. And remember, I think this is one of the best ways to do it. Like do a dry run with all of these examples, and probably you will have your algorithm right back staring at you in your face. But if you still want some hints, once we are back, I will discuss some of my theories on how we should approach a problem like this. So see you in a bit. So, all right, here are a couple of hints to get you going. So let me pick my orange marker. And yeah, if you have read the question properly, you can see that at core, this is nothing but like a string matching question. And once you're able to break it down to this, you probably start to get a lot of options. And the idea is that you are given a pattern string, and then you are given like some designs, which is a list of some things. And what you have to see is this, that if you can using these designs, like, can you make this or not? And this is a simple Boolean where you want like a true or false result back. And secondly, one of the most important things to note here is that you don't need to find all possible solutions here. Like if you read the question carefully, it just asks that can you make the design or not? So one very quick optimization that we can do here while we are trying to look up the design is that as soon as we find like one design pattern, we can just return true because we just directly found the answer. And I think thinking about these approaches, I'm thinking of we can use like a recursive approach to check like if a string can be built by a given set of strings. And let me explain you with an example. So how I am thinking about this is, let's say if we are given a set of towels as A, B, C, and AB, and let's say we have to make a simple design ABC from that. So in my head, the way to do it is that you can generate a sample tree, which would look something like this, that's starting with your three options. So you have A, B, C, and AB. And now you just have to generate like permutation and combinations of these three to generate this pattern. And how would you do that? So in this case, if you see you have picked up A, so you only have two other options where you can combine them. So for A, it can either be A, B, C, combining this with this, or it can be A, B, where you are combining this with this. Similarly, we have one with BC, and I'm going to draw it, but as soon as you see BC, and since I said we cannot revert it, you already know that this is a condition that you should not even look at because our pattern is starting with A, but we will still draw that. So here, if you see a BC can either combine with A, so can be BCA, or it can combine with BCAB, BCAB, which is another string that doesn't qualify directly because the length of our pattern should be equal to 3. And here we can see it's going 4. And the last one, similarly with AB, which one was here, I can have two patterns, one with this and one with this, where this will have, if I had to draw it here, it would be ABA and ABBC. And if you see, this is our all possible combinations that we can do with these three without reverting or doing them. And of course, we can keep building that because we are allowed to do repetitions, but this is the one that we can directly get. And we can see that here in our first combination itself, we find the pattern. So what I said with the optimization is that you can just directly return true here and move on. So I think I'm going to follow use like this. And I'm thinking that we can optimize this recursion further because looking at the input, we can see that we are given the same set of towel patterns. But we are given same set of towels, but we are given like different designs. So I think using some form of memoization may help us make the whole execution faster. Because once I build my sample search space, all I have to do it is to see that if this design is possible or not. And yeah, with that, I think I'm going to pause the video here and probably go and write some code. And I would suggest you to do the same thing as well. And once you're back, we will see if you are able to get the star using this approach. And then we will do a quick retro before moving on to part 2. So yeah, all the best. All right, welcome back. And it seems like we have received our first gold star for the first part of the puzzle. And we are closer to finding the chief historian. And if you don't know what's that all about, so from the day one, we have been trying to find Chief Historian to save the Christmas, and we have been solving all these puzzles in a hope that we will find him. So let's see that. In terms of solving this question, I actually exactly followed what I said here, and it worked really well. I think memoization was a little overkill because since we were doing an early return and we did not need to go through finding all the possible combinations, it just worked out really well. So similarly, what I did is I took a pattern and I broke it down, and from each pattern, I just called the rest of the pattern. So if A is left, so I built a function called can build, and then I passed like the rest of the pattern to C. Like, because if I'm starting with, let's say, A in this example, I already know that we can build A, but what we need to build now is BC. And then it will return me, and recursively it will break down B and C if it cannot find like a BC towel. And then it will check individually for B and C. And if I get true, true, true back all the way up, it means that we can build a towel. But yeah, with that, let's make some space here. And let's move to the part 2. Let's read it. So the staff don't really like that some of the towel arrangements you came up with, of course. To avoid an endless cycle of towel rearrangement, maybe you should just give them every possible option. We just talked about that. Here are all the different ways the above example designs can be made. Oh yeah, we did this dry run actually unknowingly here, where this example that is given here, where we found out that to make this pattern BRWRR, there are 2 possible ways. And similarly, I think they have dissected down the other ones where like BGG can only be made with BGG and R. So remember, this is our given towel types, and these are the patterns we are talking about. And GBBR can be made 4 different ways. So you can use 4 individual towels, you can use GB and a BR, you can use GB, B and R, or you can use GB and BR. And similarly, we are given another example for RR, BGBR, which has 6 different ways. And it seems like obviously those 2 towels, UBWU and this one, is still impossible because we are not changing the way we are making the pattern. But what the question wants us to do is, if I go back, the question wants us to now add up all the ways the towels in this examples could be rearranged into the desired designs, which yield 16. So this is sum of all possible combinations. And return that. And it says that they will let you into an onsen as soon as you have the list. What do you get if you add up the number of different ways you could make each design? So we really need to get into an onsen to take that path. So I think I hope the question is clear. All we need to do is that instead of returning directly true that we were doing, we just need to get all possible combinations and do a sum of that and return that. And that would be our answer for this puzzle. With that, I urge you to pause here and think about how you will modify your solution that you wrote in part 1 so that it can help you with part 2. And once we are back, I'm going to talk about some of the hints to help you in writing your code. And I'll see you in a bit. Yeah, so talking about hints for this part, let me grab my marker. So think about how, like I did the recursive approach, right? Like no matter if you did recursive or iterative, like whatever approach you followed to find all the patterns, think about how that function needs to change. In the part 1, we were just returning true on the first possible solution. But here we need to look into all possible paths. And this seems to be a theme for last few days now, where in the first one, we have a very constrained example that we do. And in the part 2, I think it just explodes into all possible paths. So, and in this all possible paths, you obviously need to do like a count and return that. So I think one of the important things if you're following a recursive solution is to be careful about the base case, like when you return and how you do the backtrack and then move forward. Because remember, in the examples that we can see on this side, you can see like there are multiple ways where we can make this. And if we consider this example that is given here, so where we have to make GBB, it says that there are 4 solutions. So if you look at this, like first you find GBB and then you do a backtrack, and you find another solution, which is GBB and where this is one towel, this is one, and this is one, and then do a backtrack, and then you find like, oh, we can make like GBBR, and where this is like 3 towels, and then you do a backtrack and you find like, oh, there is also GBBR. So possibly this gives you a great idea about how to do that. So for this approach, I think we will have to make some changes in our can build function that we were doing. And instead, I'll probably count the number of solutions, something like that, where we will keep a count of all the possibilities and we won't do an early return. And now this function would return like an integer instead of a Boolean. And a potential challenge here is to avoid overcounting the results. So your bookkeeping needs to be careful. So probably maintain a set of solutions, because there is a way to reach the same arrangement from different paths in your sample space, the same arrangement. So you need to be careful about not falling into that pitfall. And I think the other potential challenge is the combinatorial explosion that can happen with the number of possibilities that can become way too large. And this is why I think the caching will be super useful here, so that you can memorize that and you don't look into the same patterns again and again. Because if there is a sub pattern and you know that it will form a pattern below, like you can already count that, and probably you already have counted it if you cache it and look at that. But with that, I will leave you to write some code, and I'm also going to go ahead and write some code and see if we can find the answer for our part 2. And this is fairly interesting. And I don't think I'm planning to brute force here, because if you see in the part 1 also, we just directly jumped into an optimal approach, because brute forcing here will just take way too much time for us. So with that, I'll see you in a bit. And welcome back. And as you can see, we have received our second gold star. And with this, we have completed our day 19. And I did exactly what I talked in hints, no changes at all. I used the caching with recursion and just looked into all possible paths. I think caching was the game changer, because it just made my sample space a lot more smaller, because we could just, instead of going down the path, we could just return if there was a solution from there. And here I was thinking about the time and space complexity. So the time complexity for this solution would be n into m into l, where our n is the number of design strings that we were given to us. So design strings, and m is the number of patterns that was given to us, and L would be the maximum length of design. So because remember, if you are making a sample space, the length of your tree that you will form would be maximum in terms of length of your longest. So that's the worst case scenario, your longest design, because you cannot just go, you don't have to go beyond that. And caching helps a lot here with the complexity. And in terms of space complexity, since we are maintaining a graph of the possible outputs, it would be O of n into L, where n is the number of design strings and L is the length of your long design. So this is as many number of combinations that we need to store. And yeah, with that, we are at the end of day 19. And if you look at that, beautiful. I have finally caught up with day 20, 2 hours to spare. I was running behind because sometime life gets in the way, but I have now 2 videos to edit back to back. So I'll probably be doing day 18 and day 19, depending upon when you see it. But with that, I think we have reached to end of this video. If you enjoyed solving this problem with me, please like and subscribe. And if you have feedback for me, please comment below and let me know that how I could have explained it much better, and feel free to ask your questions, and I will be pushing all my code on GitHub. So take a look at that, and if you have any suggestions, feel free to raise a pull request. And yeah, so it was fun. I have really enjoyed solving last 2 days, 18 and 19. I think it got really difficult based on the gaps in my knowledge for the day 14, 15 and 16. But this one felt right at home for me, and I got to learn so much more. And yeah, I think I'm going to go ahead and edit these videos so that I can quickly get them to you. And I will see you in the next video. Take care. Bye-bye.